Hello everyone, welcome to this webinar. My name is Abtinatari. I'm an application engineer in Maplesoft. In this webinar, I'm going to show you how to model and simulate the gear shift process in MapleSim and perform some analysis to improve the shift quality. As you can see in the agenda, first I'm going to talk briefly about the gear shifting process and then the project which was defined, and at the end I will show you our approach to solve this problem. In the vehicles with manual transmission, it's the driver's responsibility to manage the right timing and provide sufficient delay for the gears to be disengaged from one state and engaged for the next state, which can be upshift or downshifting. This timing is controlled by the driver's clutch pedal. However, the design of the automatic transmissions are different. For each gear state, there are a combination of gears which should be engaged and disengaged. This shifting process produces disturbances in the engine's output torque, which can be experienced by the passengers. That's why the gear shifting in automatic transmissions is an important topic in the automotive powertrain industries. So the engage and disengage process of the clutches is usually performed by the corresponding hydraulic actuators. The hydraulic pressure applied onto the clutches regulate the torque, which can be transferred through the plates. This torque is also called torque capacity, and the means by increasing the applied pressure, the torque capacity can be increased. So to fulfill the engage and disengage process, a controller which can minimize the disturbances is required. First, let's take a look at the corresponding diagrams for the gear shift process. In this case, we have a one gear shifting upward. When the transmission operates and one gear is fully engaged, as the engine speed increases, output torque decreases. While shifting from one gear to another, this behavior changes. And two different phases are detected in the output torque, which are called torque phase and inertia phase. The first phase or stage of the gear shift process is the torque phase, where the torque is transferred from the outgoing clutch to the oncoming clutch. During this phase, the pressure applied to the oncoming clutch is increased, while the pressure applied to the outgoing clutch is decreased. As a result, the output torque decreases, while the engine speed remains constant, until the point where the oncoming clutch, which is gradually being affected by the frictional torque, starts to slip. During the inertia phase, the applied force on the oncoming clutch continues to increase. As a result, a rapid increase in the transmission's output torque is observed, as well as a decrease in the engine speed as the vehicle transitions from the low gear speed level to the high gear speed level. Now, if we take a closer look at only the output torque, the whole gear shift transition can also be called or divided into two phases. One we can say torque hole, and the other one torque overshoot. So the deeper the torque hole is, the larger deceleration or discomfort for the passengers during the gear shift. Therefore, a narrow and shallow torque hole is always preferred. In addition, the height of the torque overshoot phase corresponds to the amount of vibration transmitted to the passengers, which also should be minimized. So the objective of this project was to model the gear shift process of an automatic transmission using MapleSim, the multi-domain physical modeling and simulation tool, and analyze the gear shift quality and observe the output torque disturbances as the forces into the clutches increase or decrease. Here you can see the graphical user interface of the MapleSim. On the left, you can see the libraries from different domains. On the right, we have a 2D diagram area where we can drag and drop the components from the libraries into it and start building our model. So to model the gear shift process, we need two sets of clutches and gears, a simple engine model, and the load components and inertias. So first, from driveline library, the engine components, which is using the lookup table for the torque versus engine speed data, is selected. Then the simple dyno providing a resistive load, and then under 1D rotational library, the clutch components, which are pressed together with a normal force representing the hydraulic pressures that can be easily varied using the controllable input signal. And then two ideal gears to be placed in parallel to represent the two-speed gearbox. We also need to add some inertia blocks to model the engine output shaft inertia, and then we connect these two lines parallel to the engine from one side, and on the other side we need to have another inertia representing the driving axle inertia, and another ideal gear which will be set to final gear ratio of the gearbox and then connected to the load. Now we need to set the proper parameters for every component. As you can see, by selecting each component, its parameters can be seen and listed on the right hand side palette, which is called Inspector tab. So the ratios for the gears, the inertia, moments, the final ratio, and the parameters for dynamometer. So next we need to define two series of inputs for low gear clutch and high gear clutch, which can be achieved by adding a lookup table. So this time-based lookup table with the demox, which can read two different columns from the external source, can be sent as inputs forces to the low gear and high gear clutch components. To get the feedback from model, we can add some sensors. For example, the angular velocity sensor, which will be connected to the output shaft of the engine, and then we can add the probe to it to give us the results as a plot. We can change the name of the probe, and now in inside the sensor we want to read the RPM, so we select it and change the radian per second to RPM. So in addition to the sensors, if the purpose is only to looking at the values and not using them back anywhere in our model, we can simply attach the probes to the model. For example, in this connection, we can extract the angular velocity and the torque applied to the dyno. The same values can be read here, which we can call it the driving axle or the output shaft of the gearbox. Then we can also read the magnitude of the forces applied to each clutch, which in this case we call it low gear clutch and high gear clutch probes. So these values, as I mentioned before, are going to come from the Excel sheet or any external source which can be set in the lookup table. So how to set this value in the lookup table? You just click on it, and on the left hand side palette under project attachments datasets you can attach the file. Then you can locate your in this case Excel file which is available and attach, and as you can see it is now attached to the our MapleSim model. Let's take a look at the Excel sheet, like the worksheet itself. So inside it we have on the first column the time, on the second column the force which should be applied on the low gear clutch, and on the third column the force which should be applied on the high gear clutch. So by going back to the, and as you can see here we have some plots or some plots representing the first column and the second column based on the time. If we go back to the model, you can see by selecting the lookup table on the right side, again under inspector tab, we can define the data source. So it's right now inline, which should be changed to the attachment. And then under data you can select the clutch timing Excel sheet which was attached to data sets previously, and then the columns which should be sent out of the lookup table. So in this case the first one was the time, so the second column and third column which will be respectively sent to the top clutch and then the bottom clutch. And as you noticed in the first two rows of the Excel sheet we had some titles and labels, so to bypass those we have said skip these two rows, the first two rows. So here is the visualization window where you can have the plots of your MapleSim model generated. So after running the model with external forces inputs to our clutches, and as you can see in this left top plot we have those values of the clutches as it was defined in the Excel sheet, and then on the right we have the engine output RPM or rotational speed, and then input shaft to the input shaft speed again, rotational speed, and then the output shaft torque. Now if we go back to our Excel sheet and change the pattern or the timing of the clutch, like let's say the low gear clutch disengagement, we will get something like this. So we have more delay in our low gear clutch disengage process, and as you can see, the output torques have been changed. So if we put these two results on the same plot, you can see the red is for the first set of experiment and the dotted blue line is for the second set. And in both cases, the ongoing clutch or the high gear clutch have been kept constant. So for the cases where the outgoing clutch have been fully disengaged in 0.6 seconds, you can see we have the maximum output torque of 655 and then the minimum of 325. But for the second case where the clutch was fully disengaged or released in 1.5 seconds, so that torque minimum and maximum values have been changed to 225, as you can see here, and then 575 Newton meters here. So the reason for this much sudden decrease in the torque value is incomplete disengagements of the outgoing clutch pressure. That means both outgoing and oncoming clutch are semi-engaged, which produces the reverse torque, and the result of that is going to be the discomfort to the passenger's body. So by knowing the relationship between the gear shifting, the vibration or disturbances, and the passenger comfort, the suitable set of the values for this engage and disengage timings of the clutches can be obtained by doing the repeated simulations for number of iterations using different set of parameters. MapleSim is written on top of the Maple. Maple is a strong symbolic analytical tool which gives the user the capability of investigating any model which was built in the MapleSim. As you can see in this slide, so we have the graphical user interface of the Maple, which is already linked to our MapleSim model. So the user can easily link the model back into the Maple and start doing different analysis. For example, one of these features is the ability to compile the model while keeping user-defined parameters symbolic. This enables the compiled model to be simulated repeatedly for different sets of the parameters in a small fraction of time, when compared with having to recompile the model for each simulation run. In this slide, you can see an API command which was used during the this experiment, which is called parameter sweep. This performs a parameter sweep of the MapleSim model, which in this case the sweeping parameter was the variable delta. The delta is the offset or the delay which was applied to the oncoming clutch force. And as you can see here on the top, we have the value of the force applied to the clutches, and on the right side bottom here we have the output torque of the transmission or gearbox corresponding to each of the numbers or swept parameters, and here is only the zoom in version of this area, which gives you the more clear understanding of the situation. So as you can see, playing with these numbers and having the capability of accessing these parameters symbolically and changing them in the small fraction of time is going to help us to design the better controller, or to come up with the better numbers to improve or enhance the quality of the gear shifting. To summarize this session, a simple dynamic physical model of an automatic transmission was created to evaluate all required forces and motion characteristics of the system during the shift process, and there was an investigation of the effects of the applied pressure to the gear clutches on the quality of the gear shifting. And then the efficient analytical methods to interact with the model were discussed, which is only possible because of the having the access to the parameters of your model. And at the end, once a suitable model with the desired parameters have been created in MapleSim, the users can take advantage of the optimized code generation templates to export their model to different code languages, which can communicate with other software packages for co-simulation purposes or hardware in the loop testing. Thank you for attending this webinar.